Hi guys, this is Mrs. Gessler, and in this video we're going to talk about reaction coordinate diagrams. The purpose of a reaction coordinate diagram is to show how energy changes during a chemical reaction, and we can go ahead and write that down. Reaction coordinate diagram shows energy changes So we're going to be looking at how energy changes during a chemical reaction. Now, what this would look like as an example here, and we'll do some labeling. You start with your axes, okay? And what you have here, this would be like time. So as your reaction progresses, you're going to be moving this way. And then on this axis, your x-axis, or your y-axis, you have the energy. Often, because it usually uses a lot of energy, they usually measure it in kilojoules, which would be 1,000 joules, well, times 1,000 of whatever the number is that they put on that scale there. And it might look, well, there's kind of two options. So perhaps it starts the low energy, and as it progresses, the energy increases. It reaches some sort of maximum and then comes back down to reach another level place here. And this is going to be the kind of energy that we're talking about here is chemical energy, and that chemical energy is changing as the reactants break apart. Energy is released, and then as those products are formed, energy is absorbed, and depending on how much energy the difference is, well, then we can know how much energy changed in the chemical reaction. So this area right here represents the energy of the reactants, okay? This area right here represents the reaction progressing. And then this area right here would be the energy of your products, okay? This highest amount of energy that you have right here is called the activation energy. In order for a chemical reaction to take place, we have to reach this activation energy here. And then the difference between the products and the reactants is going to be the change in energy. Now, the nice thing about reaction coordinate diagrams is that you can easily tell if it's endothermic or exothermic because you either increased energy or you decreased energy. And this is inside, so this would be endothermic because now we have more energy than we started with. And this would be exothermic because now we have less energy than we started with. We're always talking about the materials themselves. A second example that we'll look at, we'll call this example 1. A second example might look like this, where the reactant energy and then the activation energy, and then it ends lower, okay? So in this case, this one went up, so this one was endothermic. We'll just move this exothermic down here. We still have that our energy went from here to here, so this is our change in energy, but this time you can see that it went down, okay? This is exothermic because the energy came out of the reactants. We still have our reactants here. Our products have less energy. This is what's happening, or this is the progressing reaction, and the energy is changing. This topmost point here is our activation energy. Okay, and again, we're measuring energy on the y-axis, most likely in kilojoules, and we'll have time on the x-axis here. So, some problems that you might see regarding the reaction coordinate diagram is that you might be asked how much the energy changes, how much energy is absorbed or released, okay, that how much change energy. So well, let's do an example. How much energy is absorbed? Now, in order for it to be absorbed, what kind of reaction does it need to be, endothermic or exothermic? Well, in order for it to be absorbed, it's going to have to look like this first one we drew because it has to get more energy. So this one's going to be endothermic, okay? So endothermic. And it's pretty easy to answer this kind of question. You just need a graph that has a reaction coordinate diagram that's going to look like this, okay? Maybe it's going to ask you the change in energy, not necessarily if it was absorbed. But this is going to have some value. Let's say it's 400 kilojoules. And this is going to have some value. Maybe it's 500 kilojoules. And this is going to have, that looks like maybe 575 kilojoules. So the question says, what's the activation energy? You would find this value. The energy of the products, the energy of the reactants. So if we wanted to find how much energy was absorbed, we're just looking for that change in energy. Well, how much did we end with? We'll just subtract our start. Okay, so let's see, we ended with 500 kilojoules, and we started with 400 kilojoules, which means we absorbed 100 kilojoules. These are pretty easy, right? You're probably wondering, why is this unexpected? It should be easy, right? No. Okay, so what if you had to answer the same question, but it said how much energy is released? And maybe it doesn't say whether it's released or not, and you have to figure that out. Hopefully you can gather from the graphs here. So this kind is going to look like this. And let's go with 250. This can be 200, and this can be 50. That looks good. Okay. So we're going to do the same thing, change in energy. Our ending energy here is 50 kilojoules. There's our time. I didn't label my axes, okay? Our starting energy was 200 kilojoules, so we released 150 kilojoules. There's going to be a negative on there. That negative literally means that it was released. If when you do the difference here, and as long as you're doing the end minus the beginning, if you get a negative, you know that energy was released. And that's all it is to looking at these reaction coordinate diagrams. If you have any questions, make sure you ask your teacher. Thanks for watching.